The last topic for this chapter is nuclear reactions. And if you remember at the beginning of the module, we looked at this graph of binding energy versus the mass number, and we said that iron 56 was kind of at the top as far as the most stable nucleus that there is. And so we've got two different groups, those that have a mass number smaller than that and those that have a mass number larger than that. And what are they going to do to try and get as close as possible to this and to achieve that ideal? Well, there are two types of reactions. The first one is called fusion. And fusion is what is going to happen with the atoms on the left-hand side. Because in fusion, I'm going to have small nuclei as reactants. And these small nuclei are going to fuse together, or they're going to kind of glue themselves together to try to become larger. So if I have an atom of hydrogen 2, actually if I have two of them, and I can put coefficients in front of these, just like I could put coefficients in front of any reactant or any product, those two will fuse together and they will form an atom, that would be cool, and an atom of helium, and they're also going to have a leftover neutron. Okay, so this product is larger than what I started with, so they have fused together. Okay, another example of that would be if I have an atom of deuterium and an atom of tritium. Now those other names are just, deuterium is the name for an atom of hydrogen that has one neutron along with its proton, and then an atom of tritium has two neutrons along with its proton. Those will actually also fuse together and give me an atom of helium, and they will release a neutron. Okay, so that's fusion, and that is what's going to be the case on this part of the graph. Fusion's going to happen over here. Okay, this releases an amazing amount of energy, and it's not unlike the second type of nuclear reaction, which is fission. And fission is the opposite of fusion. In fusion, I'm taking atoms, taking nuclei, and I'm putting them together. In fission, I'm taking them and I'm splitting them apart. And so that's what happens on this side, where I have these large atoms, and they're going to split in order to try to make an atom that's more stable. So in fission, I have large reactant atoms. Okay. This is the type of reaction that's going to be used in your nuclear power plants, in nuclear bombs. And the main reason for that, you'll read in the last section, it's mainly because we just don't know we don't have the technology yet to be able to do anything with these fusion reactions in order to be able to create the energy that we need. It takes so much energy to cause them to react that we actually are producing very little for the amount of energy that we're putting into it. So right now, we have the technology for this, but not for this, and you'll read about that later, okay? An example of a fission reaction is uranium, 235 over 90 to uranium. And what you do is you actually shoot neutrons at this very large nucleus. So if I shoot a neutron at it, shooting that neutron in there will actually take this very large nucleus and cause it to split. And so in this case, what it makes is 141 over 56 barium, and it will make an atom of krypton, and it will make 3 more neutrons. Okay, so you can see that here I have a very large nucleus, and then by shooting that neutron on it, I've made 2 smaller nuclei. Now what happens then is these 3 neutrons that have been produced can then go and strike more uranium atoms and cause the reaction to continue. If you have a critical mass or the right amount of this, then you can have a reaction that is sustained and continues to produce power. If you control the reaction, then you can facilitate nuclear power being produced by a nuclear power plant. If, however, this reaction gets out of control, then you're going to have a situation where you have a bomb, where the reaction literally does go out of control. Both fission and fusion are extremely exothermic, but in place of me kind of standing here talking about all these things, I figured you would actually probably learn it a lot better by looking at some other videos and going through some of the simulations that I have attached for you. So you'll be able to go through those and understand those processes in terms of power plants and bombs and critical mass and all that type of stuff much better from going through those simulations. So you'll be doing that tomorrow. We can go ahead and work a couple of other problems though, just to make sure that you know what you're doing with these reactions. So if we'll look at example 14.3, we're supposed to fill in the blank for how many neutrons are going to be reduced from this reaction. So example 14.3, I have two tritium atoms, and they are going to make 4,2 helium plus how many neutrons are going to be produced. So how do you go about figuring this out? Well, it's basically just like we did before, and you're going to have to make sure that the numbers on the top stay the same, numbers on the bottom stay the same. Okay, so if I look at the bottom, I have 2 times 1 is 2 here, and I have 2 there, so that makes sense because I'm going to have a 0 on the bottom anyway. On the top, I have 2 times 3 is 6, and here I have a 4, so I need 2 more in order to make that balance. So there's going to be a 2 in that blank. Okay, so this was an example of a fusion reaction, and then the other example as a part of this is a fission reaction. So in this fission reaction, 1, 0, N plus something is going to give me 112 over 45 RH plus 123 over 49 IN plus 3 neutrons. Okay, so if I look at this, 0 here, 0 on the bottom here. So if I just add these two together, if I add 45 and 49, I'm going to end up with 94 on the bottom. And so from the periodic table, I know that 94 is an atom of plutonium. Then I have 112 and 123, and I have 3 times 1 on the top, which is another 3. And so that, if you add all that together, that's going to give you 238. But I have 1 neutron over here, and so that means that the mass number here is going to be 237. So again, balancing these is just really a matter of doing the arithmetic and looking at the periodic table to get the appropriate element for your atomic number. Okay, so those are nuclear reactions, fission and fusion. Enjoy going through those simulations, and I'll see you back here then for module 12.